Hello everyone. Today we are going to discuss the topic dimensional analysis for class 11th physics. In this topic, we will study the 7 dimensions corresponding to 7 fundamental physical quantities in the International System of Units. We represent the dimensions within square brackets. So, for length, the dimension is written as capital L within square bracket. For mass, we write the dimension with capital M within square bracket. Similarly, for time, we use capital T within square brackets. For electric current, we use A because the SI unit for electric current is ampere. Therefore, dimension is written as capital A within square brackets. For thermodynamical temperature, the SI unit is Kelvin. So, the dimension is represented as capital K within square brackets. For luminous intensity, the SI unit is candela. So, the dimension is represented by CD with C capital within square brackets. For amount of substance, the SI unit is mole, that is MOLE, but we use only the first 3 letters to represent the dimension within square brackets. Now, how do we define the dimensions? The dimensions are defined as the powers or the exponents to which base quantities are raised. For example, formula for volume is side cube. For a cube, we use side into side into side as the formula. So, the dimensions will be L cube within square bracket. That is, volume is said to have 3 dimensions in length. But as we can see that there is no mass and time in the formula, therefore we can say that volume has 0 dimensions in mass, 0 dimensions in time, and 3 dimensions in length. The formula for velocity is displacement upon time. The SI unit of velocity is meter per second. So, the dimension will be L by T. That is, we can write the dimensional formula as m to the power 0, L to the power 1, T to the power minus 1. Now, what are dimensional equations? When we equate a physical quantity to its dimensional formula, then we obtain a dimensional equation. So, for volume, if we write volume in square brackets on left hand side and on right hand side we write the dimensional formula, then we say we have written the dimensional equation. Now let us find dimensional formula for some more physical quantities. Acceleration, as we know, the formula is change in velocity upon time, and SI unit is meter per second square. So the dimension is LT minus 2. That is, the complete dimensional formula will be m to the power 0, L to the power 1 and T to the power minus 2 within square brackets. Do not forget to write the dimensions within square brackets. For force, we know F is equal to ma, Newton's second law of motion. Unit of force is kg meter per second square. So, the dimensions will be 1 dimension in mass, 1 dimension in length, and in the denominator we have 2 dimensions in time. So, the dimensional formula will be m to the power 1, L to the power 1, T to the power minus 2 within square brackets. And if on the left hand side we write force within square brackets, then we have written the dimensional equation. Now, there are 4 types of quantities: dimensional constants, dimensional variables, dimensionless constants, and dimensionless variables. Let us discuss these four types of quantities in detail. Dimensional constants are those quantities whose values are constant and they possess dimension. For example, velocity of light in vacuum. Velocity of light in vacuum has a constant value 3 into 10 to the power 8 meter per second, and dimension will be same as that of velocity, that is L t minus 1. Similarly, we have other examples which are constants and they possess dimensions. Boltzmann constant, universal gravitational constant, etc. Now, the second type of quantities are dimensional variables. Quantities whose values are variable and they possess dimensions like area, volume, density, velocity. All these quantities are variable and they also possess dimensions. So these quantities are dimensional variables. The third type of quantities are dimensionless constants. These quantities are constants but they do not possess dimensions. For example, pure numbers 1, 2, 3, etc. They are constants but they do not possess any dimension. Pi, which is also a mathematical constant, does not possess any dimension. The fourth type of quantities are dimensionless variables. Quantities whose values are variable and they do not possess dimensions. Angle, strain, specific gravity. These are some examples of quantities which are variables but they do not possess any dimension. Now let us discuss a question. Can there be a physical quantity which has no units and no dimensions? Yes, the answer is we can have a physical quantity which has no unit and no dimension. Strain is the physical quantity which has no units and no dimensions. Another question can there be a physical quantity which has units but no dimensions? Yes, angle is a physical quantity which has units but which has no dimensions. All quantities having dimensions also have units. This is a very important concept to note. Whenever we have physical quantities which has dimension, then it must also have units. So, if a question is asked to you, can there be a physical quantity which has dimensions but no units? Then you must understand quantity having dimensions must possess units also. What are the uses of dimensional equations? We have discussed the dimensional formula and we know how to write dimensional equations. But what are the uses of these dimensional equations? Let us discuss. There are three uses of dimensional equations. First, conversion of one system of unit into another, checking the accuracy of the formula, and derivation of formula. These three are the uses of dimensional equations. Let us discuss these three in detail. Conversion of one system of units into another. That is, if we have a quantity in a given system of units and we want to know its relation in the other system of units, then we can use the method of conversion. Now we know that the magnitude of the physical quantity remains same in all system of units. So we can write Q is equal to N1U1 is equal to N2 into U2. Now what are these U1 and U2? These are the units of measurement. And what are N1 and N2? These are the respective numerical values. So, in one system of units, we can write U1 as equal to their mass, length, time raised to the power of the bases A, B and C. And in other system of units, we can write U2 as equal to M2 to the power A, L2 to the power B and T2 to the power C. Now what are these A, B, C? These are the dimensions of the physical quantity in mass, length and time respectively. These dimensions are same in all the system of units. So we can write same powers A, B and C. Now how to convert? Using the note that Q is equal to N1U1 is equal to N2U2, we can write the equation and solve. We will get N2 is equal to N1 M1 upon M2 to the power A, L1 upon L2 to the power B and T1 upon T2 to the power C. How can we find relation between SI and CGS units of force? That is, 1 Newton is how many dyne? We know in SI system, unit of force is Newton and in CGS system, the unit of force is dyne. Now how can we find the relation between the two using this method? We will write the powers of A, B and C, that is the powers of mass, length and time, that is the dimensions. So the SI unit of force, as we know, is kg meter per second square. So the dimensional formula is m to the power 1, L to the power 1, T to the power minus 2. Therefore, we write A is equal to 1, B is equal to 1 and C is equal to minus 2. On one side, we write the SI system and on other side, we write the CGS system and we write the corresponding values of mass, length and time. In SI system, mass is kg, length is in meter and time is in second. In CGS system, mass is in gram, length is in centimeter and time is again in seconds. So we have the values of M1, L1, T1 and the corresponding values in the second system of units. Now we use the formula that we just derived. Substituting the values and solving, we will convert all the units in a common unit. That is, we will convert kg into gram. As you can see, we have converted 1 kilogram to 1000 grams. We have converted 1 meter to 100 centimeter. And by further solving, we get 10 to the power 5. So we can write 1 Newton is equal to 10 to the power 5 dyne. Can we check whether the formula that we have written is correct or not? This is the second application. Yes, of course, we can check the formula, whatever we have written is correct or not. How can we check the accuracy of the formula? We can check the accuracy by keeping the following points in mind. Powers of mass, length and time are same on both the sides of the formula. And we follow a principle of homogeneity. It is very important to note that only the same dimensions can be added or subtracted. So if we add dimensions of same quantity, that is length plus length, we will get the same dimensions of length only. For example, you travel a distance of 5 meter, then you again travel a distance of 7 meter. So total you have traveled 12 meter. So the dimensions remain the same. So L plus L should give you L. Similarly, L minus L will also give you L. This is very important to understand. Third thing is, a dimensionally correct equation may not actually be the correct equation, but a dimensionally incorrect equation will always be wrong. So, while checking the accuracy of the formula, we must understand if the dimensional analysis gives us the result that the equation is dimensionally correct, then it is not necessary that the equation is also correct. That is, a dimensionally correct equation may not be the actual equation. Now let us solve one problem. We know the equation of uniformly accelerated motion v square minus u square is equal to 2as. Now let us see what are the dimensions on the left hand side and the right hand side. On the left hand side we have velocity square, that is v square. Again we have minus u square. So according to principle of homogeneity, the same dimensions only can be added or subtracted. So here the dimension of velocity is lt minus 1. So we can write lt minus 1 within square brackets. We have square. So we write lt minus 1 whole square minus lt minus 1 whole square. This will result in the same dimension. So finally when we use the squares, then we get L square t minus 2. On the right hand side, I have 2 into acceleration into displacement. 2 is a constant. It will not have any dimensions. Acceleration unit is meter per second square. So the dimensions will be L t minus 2. And for displacement, the dimension is L. So on solving, we get L square t minus 2. Therefore, left hand side and right hand side show that the formula is dimensionally correct. The third thing is, can we derive a formula using dimensional analysis? Yes, using the principle of homogeneity, again, we can equate the powers of mass, length and time on both the sides, and we obtain 3 equations which can be solved for 3 values. Let us do one question. If we have a question in which we have to derive the formula for centripetal force using the method of dimensional analysis, then we must know on what factors centripetal force depends. So, centripetal force depends on mass, velocity, and radius. Now let us solve this. We assume that force is equal to a constant of proportionality into mass to the power A, velocity to the power B, and radius to the power C. Now we will write the dimensions of all the quantities on left hand side and right hand side. As we write the dimensions of force mlt minus 2 on left hand side, and on right hand side we will write the dimensions of mlnt. M to the power A for mass. Velocity is Lt minus 1. So Lt minus 1 raised to the power B. Then radius. Radius is length. So L to the power C. And when we solve by using the concept, when bases are same, powers are added, we get M to the power A, L to the power B plus C, and T to the power minus B. Now equating the powers on both the sides, we get A is equal to 1, B plus C is equal to 1, and minus B is equal to minus 2. Further solving, we get the final formula F is equal to K mv square upon R. We have discussed 3 applications of dimensional analysis. Now, the question is, are there any limitations of dimensional analysis? Yes, there are certain limitations of dimensional analysis. If there are more than 3 unknown variables on which a given physical quantity depends, then we cannot solve using dimensional analysis, because when we equate the powers of mass, length, and time on both the sides, then we obtain three equations. But if we have more variables, we cannot solve these equations. The second thing is, it does not give us information whether the physical quantity is a scalar or vector. It does not tell us the value of the constants. It does not tell us the exact form of the relation when it comes to more than one part on any side of the equation. It cannot be used for deriving logarithmic, trigonometric, or exponential relations. And a very important thing is, dimensionally correct equation may not always be the correct relation, because there are more than one physical quantity having same dimensions. For example, work and torque have same dimensions. Thank you.